conference will now be recorded.
So let's start with the session. So today we'll be having the demo session for the ARM V8 architecture and the instruction set architecture training. Okay. So first let me go through the training schedule. We'll be having the training over a duration of 6 weeks. If required, we'll extend it by another 1 week. We'll be having sessions on both Saturday and Sunday, around 4 hours per day. We'll try to have timings between 10 a.m. to 2 p.m. But the same course will be available in e-learning mode also in case people are not able to attend in live training. As you see, ARM has multiple aspects that can be learned. So it could be like understanding the subsystem architecture and core architecture, even the core link, the interconnect based on ARM architecture, and even ARM instruction set architecture. So this course will focus on all these major aspects, okay, and including the subsystem architecture, the V8 specific features, the version 8 specific features, and it will focus more deep into the programmer's model, instruction set. What are the new additional instruction sets have been added over the different ARM architectures? We'll focus on that. And this instruction set architecture particularly is more relevant for people working in SOC verification, because the people working in SOC verification may not have to go deep into the design code of the development of the processor, design of the processor. They may not be much interested, but rather working in SOC verification, you need to have a good understanding of the ARM instruction set, the different execution levels, and how this maps to the different different operations of the ARM. So all those aspects need to be learned. So in that context, ISA instruction set architecture will be very relevant. So we'll spend more time on this aspect as well. Okay. Now coming to the agenda, we'll first start off with understanding some basics of SOC architecture. Then we'll move on to understand some ARM processor basics. Then we'll see how the ARM architecture has evolved from ARM 1, that is version 1, to version 9 that we are currently using. Then we'll also discuss about typical ARM CPU subsystem architecture, what is meant by big little architecture. We'll discuss that as well. Then we'll also talk about how does ARM core architecture looks like. What are the internal aspects of a ARM core? Then we'll talk about what is core link, and we'll also discuss about the ARM tool chain flow. So where we'll talk about what is compiler, linker, and assembler. Then we'll talk about ARM programmer's model. What are the general purpose registers, and what are the configuration and status registers, and what are the additional extensions like floating point registers. All those things we'll discuss. And we'll also talk about ARM instruction set, different instruction categories, and what are the mnemonics that are used for each of these instructions. We'll also talk about the instructions that are meant for 32-bit data processing, the one which are meant for 64-bit processing that are used in ARM V8. As you're aware, in ARM V8, the new set of instructions have been added to support 64-bit data processing. So we'll discuss on that. That is called as AR64. 32-bit processing is called as AR32. We'll talk about both the aspects. We'll also talk about thumb and thumb 2. These are not things that are added in V8. These have been added earlier versions. We'll talk about what is meant by thumb instructions, what is meant by thumb 2 instructions. Then we'll also talk about ARM execution states, what is meant by ARM execution state, ARM execution state, thumb execution state, and Jazil DBX. Okay, this is for Java bytecodes. This is used. We'll also discuss about this. Next, we'll talk about Keil embedded development tools. How to use Keil embedded development tools to implement the ARM-based assembly codes, and how to execute them, and how to analyze those examples. We'll discuss about those aspects as well. Then we'll also discuss about ARM V8 particular processor execution states. like what is ARC32, ARC64, how do we switch from one execution state to another execution state. Then we'll talk about secure mode and non-secure mode, and in that context we'll also talk about what is ARM trust zone. Then we'll talk about exception levels. Yeah, there are ARM V8 based process can work in 4 exception levels: exception level 0, exception level 1, 2, 3. So what is the significance of this, and how do we switch from one exception level to other exception level, also we'll discuss. And how is it relevant for moving from secure to non-secure. I mean, exception levels are all relevant for all the switching of one state to another state. We'll discuss all those aspects. Then we'll also discuss about some system instructions, then how the ARM implements exception and interrupt handling, privilege and exception levels we'll talk. That is nothing but the same topic. Then in the interrupt handling, we'll talk about what is generic interrupt controller, what is nested vector interrupt controller. You might have heard JIC and NVIC. So JIC is used in application series based process. For other things, we use NVIC, nested vector interrupt controller. So that is used for Cortex M series process. Then we'll also talk about CPU interfaces. Then we'll also talk about ARM memory model. I mean, ARM, how the ARM views the memory. I mean, whatever memory that is there, it can be viewed by different attributes, like whether it supports that part of the memory. Does it support gathering or non-gathering? Uh, does that memory support reordering or doesn't support reordering? Does it support early acknowledgement? So there are, based on that GRE, memory models can be classified into different categories. We'll also discuss about that. Then we'll also discuss about the concept of virtualization, the trust zone. Then we'll discuss about cache coherency, uh, and what is the MOESI state diagram that is used for maintaining the cache coherency. We'll discuss. We'll also talk about some operating system basics and the memory management unit. We'll talk memory management unit is something which is used in ARM application series process. For other process, we don't need memory management unit. There we use memory protection unit. So what exactly is the difference, and what are the memory protection unit provided attributes, we'll discuss. Then we'll talk about how the power management is implemented in ARM processors. Then we'll talk about ARM core site architecture. Then we'll take assembly program examples. I mean, this need not be the exact order. Instead of keeping it towards the last sessions of the training, we'll keep somewhere in between. As we are doing ARM instructions, we'll parallelly do some assembly programming examples, assembly coding example, assembly instruction coding examples, which could be some generic things that we do day to day in C program, like prime number generation, sorting algorithms, factorial. So these kind of things, we'll develop a C-based program algorithm, and then that will port it into ARM assembly code. Then we'll finally talk about the Cortex A55 cluster architecture. So this is all I plan to cover as part of the ARM V8 architecture training. If you feel that some other topics need to be included, please suggest. I mean, need not be now. You can even later, anytime during this training, you can suggest me that these topics could be included in the training. Okay. So do you have any questions before we move on to the first aspect of the today's session? Okay. So first, let's start with understanding a generic SOC architecture. In that, we'll try to understand the significance of the CPU subsystem, because we have the participant from different backgrounds, someone with higher experience, someone who are beginners in the VLSI. So considering that, we'll try to cover all the aspects from the basics and then try to move on to the advanced aspects. Um, okay, let me take one of the questions. So I have just started working in x86 based company. Will this course still be helpful? Yes, this course will be helpful. Even the companies which are based on x86, they are also trying to their architecture also have been trying to adopt risk based architectures, right? So because of the way the risk-based architecture are more efficient compared to CIS-based architecture, this course will be relevant for anyone for that matter. Even for someone who has never worked in, SOC verification, or even has never worked on at a processor level, would still this course would still be relevant, because this course would give a bigger picture of how SOC works, how the processor works, and I intend to make it a very comprehensive course. Um, Something where, because as you know, even if you want to learn few things, there are many resources available on internet, even in the YouTube to learn. I wanted it to be comprehensive, where this one course covers all the major aspects of the ARM v8 architecture. Now, to answer your question, even if you are working in x86 based company, this course would still be relevant for you, because you could still correlate. How does the typical x86 based process differ from the risk based architectures, all those things. Any other questions? So first, let's start off with sure. I will see, mostly I'll try to cover Cortex M4, M7. Yeah, but major focus will be in the application series process, because that is where all the complexity is present. Once you can learn application series process, M series is a relatively easy things to learn. But we'll try to have sessions to focus on those as well. So first, let's start with understanding of the generic SOC architecture. Okay. This architecture, do you see, uh, it has got a FlexNoC top level interconnect. FlexNoC is one of the company, one brand, one kind of company which it's by Arteris. It is this company provides FlexNoC top level interconnect. Okay. This interconnect has various master and slave components connected to it, as you could see in this diagram. It has got CPU subsystem, uh, Vishnu Varshini. ARM protocols will not be covered, like protocols like AXI, ACE protocol, Chai protocol. We won't be going deep into it. That's a different thing altogether. Here, the focus will be on ARM architecture, V8 architecture, and ARM instruction set architecture. That's all. We won't be going deep into the protocols. Now coming back to this generic SOC architecture, why I'm calling this generic SOC is, it is not specific to any SOC, mobile SOC or anything. Typically, how would an SOC architecture looks is what we are discussing here. In this case, you can see that there is a CPU subsystem connected here. You have got some design specific subsystem like GPU subsystem, which has 3D graphics. Then it has got DSP subsystem and application IP specific subsystem. Then we have got different encryption and graphics and MPEG related components sitting into one subsystem. Then we have got a memory subsystem, which has got memory scheduler and memory controller to connect to the wide IO and LPDDR3 kind of memories. Then we have got a high speed wired peripheral subsystem, which has got various things like USB 2, USB 3 with the corresponding PHY, the PCI Express controller with the corresponding PHY, Ethernet core with corresponding PHY, and then we have wireless subsystem with support for Wi-Fi, GSM, LTE, LTE Advanced. Okay, then we have crypto firewall block and RSA, PSS, and then we have got that is security subsystem. Then we have another subsystem, that is IO peripheral subsystem, which has got its own interconnect to connect HDMI, MIPI, display, PMU, JTAG. So this is what a typical SOC architecture would look like, and each of them becoming internal, next level of level 2 interconnects. This is the level 1 interconnect, this is the level 2 interconnect. Okay. Now in this whole thing, CPU subsystem plays a very important role, as we are all aware, because CPU subsystem is the point of interface between the operating system or software and the hardware. So in that, if you see this one, it has got a multi cores. The very point of multi-cores is what? Can someone tell me what is the advantage of having multi-core here? Why not just one A15, or why not just have one A7?
Multiple requests can be served to at the same time.
Okay. As you're aware, each core at any point can run one thread, right? One process. So having multiple cores, of course, it would help run multiple threads concurrently. So essentially improving the overall bandwidth of the system. Okay. Let's try to understand. So this kind of architecture, what we see, where there are four A7 cores. One core means one processor core. So four A7 cores are there, two A15 cores are there, each with its own, each of them having their own cache, L1 cache. So there will be an associated L1 cache here, L1 cache, L1 cache, L1 cache. Here also L1 cache, L1 cache. Here there is L2 cache, here L2 cache. So with each processor core, there is an L1 cache which is further divided into L1 instruction cache, L1 data cache, and one cluster of cores. These multiple A7s is called as one cluster, has an associated L2 cache. This cluster of cores, that is two A15s collectively called as a cluster, A15 cluster. This is called as A7 cluster. This A15 cluster has one L2 cache. Okay. These are connected to one coherent cache coherent interconnect. It can have its own connected L3 cache. So the L3 cache is connected to the coherent interconnect, and there is a snoop control unit or coherency unit, right, which will take care of the coherency between all these caches. Majorly it does the coherency management between L2 caches and the L3 cache. But the coherency between L1 and L2 is internal to the CPU subsystem. How they maintain coherency is internal to the CPU subsystem. What exactly is the coherence here refers is uh, to improve the overall system performance. Each processor or each cluster maintains its own copy of the data, which is a quickly fast accessible memory. Since it is close to the memory, the data can be accessed quickly. So the frequently accessed locations are cached in the L1 and L2. That improves the helps in reducing the access latency. While doing that, coherency refers to a concept where if this is maintaining at location 100, if this is also maintaining location 100, address location 100, both should be maintaining the same data. I mean, when A7 fetches the data at 100, A15 fetches data at 100, both should get the same data. It should not happen that A7 gets some data and A15 gets a different data when both of them are accessing the same address location. So that to maintain that coherency where all the processors have the same view of the data is what we call as the cache coherency. That is taken care by coherent interconnect. It has got a few components inside: snoop control unit, cache coherency, snoop control unit, and the coherency logic, okay, which will take care of maintaining that coherent cache coherency. Okay. This architecture is typically called as big little architecture. I mean, it has got few high performance application series processors, a few relatively low performance application series processors. So let's briefly talk about what is this big little architecture is all about. I mean, this is what you most of the time come across in complex SOCs. If you consider some other type of SOCs, embedded application based processors, you won't have this multi-core applications because there you don't need multiple threads to run. If you take an example of a microwave oven or washing machine, which is a consumer electronic, right, electronics, there you don't need to run any multiple threads because it is more of mechanical device. Being the electronics plays less role there. It is just used to set the mode of the operation of the that entire device. So in that case, you don't need to run multiple threads. So there we don't need multiple processor cores. So there the entire process is much simpler. You don't need lot of cache coherency concepts. Many concepts which are applicable to application series processor, like something that is used in our mobile phones, will not be relevant and required for M series, that is embedded series processors. Right now, whatever we are talking, this big little architecture is relevant for application series processors. That what we have seen in the previous slide. That is A7, A15. A here stands for application series. Next. So first, let's talk about what is this big little architecture. Big little means a few high performance processors making one cluster of the processors, few low performance processors. So yeah, whatever architecture we have seen, it has got two A15 processors. They are high performance. They are used to run high performance applications. Then four A7 processors, which are used to run low performance applications. Now there is no restriction that you should always have two A15, four A7. There can be any combination is possible. And we can also have octa-core CPU subsystem, which can have four Cortex A57 processors that makes one cluster, that is high performance cluster. Then we can have four Cortex A7 processors, a low performance processor. So Cortex is a standard trademark of the application series processors. In octa-core 8 cores, each core has its own specific thread. It can run its own specific thread. For example, you are opening a PowerPoint presentation. Okay, a processor needs to execute the corresponding instructions to invoke and run the application. So like that, I could be doing, see, in my laptop, which is a multi-core processor subsystem, I could be running multiple threads parallelly. For example, one thread is the training that I'm running, one thread is the presentation I'm playing. So there could be multiple things that could be happening. So that is where having multiple cores will help. Okay. Now, as we discussed, what is the need for multi-core subsystem? It runs multiple execution threads concurrently. Application can be, as you know, some application can be high performance, which require high bandwidth, or some can be low performance. So the high performance applications will be scheduled to run on the high performance cluster. Low performance will be scheduled for low performance cluster. And who makes that decision? Can someone tell me, if I have this kind of system where I want to open a presentation, or I want to play I want to play a movie file, which how does who decides that that should be run through A15, that should be run through A7? So what in the system decides that? Can someone tell me?
Operating system.
See, OS will have one scheduler. Every operating system will have a scheduler which takes care of the decision making. See what happens once you start your system. Let's take an example of laptop. You have a reset button. Once you reset the laptop and power up, what happens? There is a boot code which is present in a ROM, read-only memory, which is a non-volatile. So even if you switch off the memory, switch off the power to the system, that boot code will not get erased. So first what happens? One of these processors, let's say A7 or A15, one of them will boot up through boot code. Then it has got after boot code, there will be something called as bootloader. That bootloader instructions will be run. As part of that, operating system kernel will be loaded into the memory, into the system memory, that is into the DDR. Let's again repeat the steps. First you applied reset, so the processor gets starts running the instructions from the boot code. After the reset, from the boot code it jumps to bootloader. From the bootloader it fetches the kernel from my storage to DDR. There will be something called as scheduler. That scheduler will be responsible for scheduling whatever applications you are invoking on different processors. Okay. Okay. There is a operating system scheduler which takes care of that. Which process to run which thread. So kernel of the operating system has scheduler. So this is the primary decision maker for task execution. A scheduler uses different algorithms. I mean, it could be round robin algorithm, the first priority. I mean, there could be some different algorithm that uses to determine the order and placement of the tasks on available processor units. I mean, which process to run on which core is all decided by the operating system scheduler. Next. So this is one example where we have seen octa-core CPU subsystem, where I have got Cortex A57 cluster, Cortex A53 cluster. So There will be L2 cache here. There will be L2 cache associated with these two cluster. So the coherency unit, that is CCI, cache coherent interconnect, maintains the coherency there. In the later part of the today's session, we'll discuss about what are the internal components of the cluster. I mean, there are majorly three things that make up every cluster. We'll discuss all those things as well. Then, as I said, if you are running a low load applications, okay, that will be run through A53 cluster. On a high load applications, that will be run on the A57 cluster. Yeah, Guru, please ask your question.
Sir, how between two clusters, cache coherency will work for coherency of cache, but within same cluster, how L2 and L3 are coherent?
Let me check my audio settings. Yeah, Guru, please ask your question now.
Sorry. So between two clusters, I understood CCI will help for cache coherency.
Yeah.
But within same cluster, suppose L2 and L3 have a different data, how the coherency will be taken care?
No, you mean L1 and L2 or L2 and L3? Can you come again?
L2 and L3, sir.
No, L2 and L3 is also taken care by coherency interconnect. For L1 and L2, it is internal to the cluster. So cluster will have a logic internally to take care. But between L2, L3, see, here is the L2, right? Here I have L2. Here I have L3.
Okay.
So that will be taken care by a coherent interconnect only. It generates some kind of snoops. Through that, they will get the update.
Okay.
Anytime this generates a access, this Snoop control unit notices that there is a transaction happening to that address. It generates the Snoops to other things. And here it doesn't even generate the Snoop. This coherent interconnect itself is the master of that. So it directly updates that. Whereas here it generates a Snoop. One of the processors, which will be identified through some logical processing unit. Okay. Through that, they will update that L2 data. Because some update has happened, they will reflect the changes into L2 cache accordingly.
Okay.
So your question should have been more L2 and L3 is automatic because coherent interconnect can work with L2 as well as L3. But for L1, coherent interconnect doesn't control that directly. There is some cluster internal specific thing that maintains the coherency between L1 and L2.
Okay.
So just a question on the same. So for L1 and L2 also it should be like with the snooping mechanism, or it has its any own internal logic that they can implement?
It should be specific internal thing. The Chai protocol, DACE protocol deals at L2 and L3 level. They don't particularly talk about L1. It should be internal mechanism. Yeah.
Okay. It's not via the snooping there also it happens.
No, it's not through snooping. Yeah.
Thank you.
Yeah, maybe other question. If someone else had asked questions before, I was my audio settings were not proper, so you can repeat your questions if I missed anything earlier.
Sreenivas, were you able to hear me?
Yeah. Yes.
Yeah. So Sreenivas, one question. You said L2 and L3 will be, I mean, that coherency will be maintained by this CCI, right? And L1 has A57 is its own, instruction set which will take care of L1, right? So between L1 and L2, right, who is responsible to make sure that coherency is maintained between L1 and L2?
Between L1 and L2,
because CCI will not come into the picture, right?
CCI will maintain only at L2 level, L2 and L3 level. I'm not sure particularly which component inside the cluster. I can check and get back on that.
Okay, yeah, sure.
Next. Now let's talk briefly about the CPU subsystem. Okay. We have discussed what is big little architecture. We have discussed. In the big little architecture, A57 is the high performance application, A53 is power saving and low performance applications. It is possible to have variable number of high and low performance processors. There is no particular thing like there should be 4 high performance, 4 low performance. Any combination is possible. Even you can have a combination where you have 1 high performance processor and 7 low performance power saving targeted processors. One among octa core act as a primary core. See, when you are booting up this kind of CPU subsystem, what happens is, if you look at the overall diagram, there will be some reset. I mean, though in this diagram not shown, you know, right? There will be power clock reset management block will be there. PRCM, you can say power reset clock manager. So that will get the external reset and it generates the reset, and reset is given to one of the primary cores. Okay, that core will boot up first. That is the primary core in the system. All other cores will be the secondary cores. So the primary core has the standard process where it runs the boot code. As part of the boot code and bootloader, it sets up all the interrupt handlers, exception handlers, and after that it executes the code specific to bootloader, which brings up all the essential clocks and all the essential components for system to work, and even it brings up the DMA specific clock. And once it is done, it moves the data from storage. Let's say here I have the SSD device connected through the PCIe. So from here it configures the DMA somewhere here. Assume there is a DMA. Okay, it uses the DMA to transfer the data from my SSD into the LPDDR5. That is it has moved the operating system kernel, and then it starts executing the instructions from the system memory, that is the LPDDR3. And then once it has booted up, it starts booting up other cores by programming their registers. There will be some corresponding processor specific internal register. By programming those registers, it starts booting up other CPU cores. Let's repeat all the things again. First, we have applied reset to the system. Assume this is my laptop. You have resetted. So that reset goes to one reset handler block, or you can say power reset clock manager block, which is responsible for generation of the clock, generation of the reset. In this case, since we added power also, it is also responsible for dynamic power management of the system. Now, talking about things specific to the reset that went here gets distributed to all the other components in the SoC. So one of these reset also goes to the CPU subsystem. In this CPU subsystem, the reset doesn't take effect for all the cores. It will take effect only for one of the cores, what we call as the primary core. And every SoC has one of the cores designated as a primary core, which doesn't change. Okay, dynamically it is fixed at the time of manufacturing of the device. So because of the reset, that primary core, assuming that this A15 is the primary core, it starts the process of boot. So whenever you apply reset, it has got one program counter that is set to a specific location, which is pointing to reset handler. Once it points to that location, it starts running some instruction called as reset handler instruction. Because you applied a reset, it has to run instruction specific to reset handler. As part of that, it sets up various interrupt vector handler locations and other exception handler locations. Then it starts executing a specific code called as bootloader. As part of the bootloader, it will configure all the required clock. Because let's say I have a DMA somewhere here, assume one DMA is connected. For DMA to work, its clock should be running, right? Without clocks running, my DMA cannot do the data transfers. Here DMA, as you would be knowing, it is the direct memory access we are referring to. So these kind of essential clocks will be enabled. Even for me to access PCIe clock should be running. LPDDR3 clock should be running. So that is all taken care as part of the boot code and bootloader. I would say majorly bootloader. Okay. So what bootloader does is it configures the clock controller to ensure that these clocks are running. Whatever clocks which are essential for system to boot it up are all running. Once these clocks are up, it programs my DMA controller, DMA engine, to start moving the data from SSD device. My solid state drive will be present here, which is connected through the PCI interface to the system. So this is where my C drive, D drive, all the data is present in my laptop, right? I mean, in that case, it moves the operating system scheduler, the kernel, entire information into my LPDDR5, LPDDR3. So once it is done, this will intimate the A15 that I have moved the data. Then along with that, once it is done, it also starts booting up other CPUs by programming particular registers inside those corresponding processes. Then once all the things are up, then the operating system scheduler knows that all these cores are up. So anytime you are invoking an application, this scheduler now knows that to whom I need to schedule the activity. Let's say you're opening a presentation. Should I assign it to A15? Should I assign it to A7? I want to play a movie. Should it be assigned to A15 or A7? So based on the what is the application requirements, bandwidth requirement, it will decide which CPU core to use. So this is a very brief about how this multi-core CPU subsystem boot up happens. We discussed about this. Okay. As I said, one among octa-core acts as a primary core. Remaining 7 cores are secondary. So primary core boots up on reset. So it will be through the reset, it will boot up. Other cores will boot up by programming their corresponding registers, where we may set their corresponding reset handler location and all those things. So this was a brief about ARM CPU subsystem. Yes, Sreenivas, please ask.
Who decides the primary core out of all the cores? Which core will?
It will be decided at the architecture level only.
So
It
it
is,
will be same for all, means every time I boot up my laptop, that core will be fixed, or each
yes,
time, or
that core will be fixed. That will be the fixed. It won't, as I said earlier also, right? It will be fixed. It won't keep changing.
So at
Now let's
the platform level,
yeah.
they will add it as a primary core always. So how that?
Yeah, one of the cores they will designate as a primary core. Other cores will automatically behave like secondary cores.
Okay, that information how the reset handler will be knowing and loading the.
No, it's not the reset handler, right? It's the reset, how the reset is routed to them corresponding.
Right. So that
One
is
is
like a hard coded path kind of thing.
hardware specific thing.
Okay.
Basically, what is reset handler? You would be aware, right? See, reset handler is nothing but a set of instructions that CPU core has to execute. Now, when will CPU core start executing? Whenever you set that that CPU core will have a corresponding program counter. Each CPU core has PC register, right? Program counter register. So when that PC is set, let's say I set it to 0x00000004, for example. So this is where assume reset handler is present. So you are telling to the CPU core that CPU core is being informed to run instructions starting from this location. Okay, this is where that reset handler will have then the pointers to all other vector handlers, interrupt vector handlers, and everything. What we are telling is when reset comes, when reset is applied to CPU subsystem, entire CPU subsystem, only one of them gets resetted. One of them gets resetted by means of reset, by means of this hardware reset. Others will not get resetted. Once this primary core is up, then it programs the other CPU, other cores registers to boot them. I hope it clarifies.
Yes. Yeah. Clear.
Sreenivas, one question here. Yeah. So you said only one code will get resetted, right? Is that the correct understanding? So let's say multiple cores are running in parallel, right? And some instruction is getting executed, right? Now, if reset in between hard reset came, right, and if it is only given to the one particular core, right? So the threads which are running on other cores, what will happen to them?
That
Because
should also happen, but I think it's related to boot up. Let me come back to you with that. What I got to your question. Let's say they're running,
yes,
and at that time you apply reset. It should reset
yes,
other things also, but
yes,
boot up process. I think yeah, I'm probably contradicting myself. So yes, reset should apply, but the boot process, primary core will boot through reset, and other cores will boot through means of register programming. But let me come back to you with the more clarity in the next session on this.
sure, sure, yeah.
Now let's move on to the next topic, that is SOC verification. Very brief about SOC verification, and here we'll again try to understand the significance of the CPU subsystem in a SOC verification perspective. Okay. Let's understand typically how an SOC execution works. I mean, when you're running an application, so what is the role of different components in that, and in that, what would be the significance of the CPU subsystem? Okay. Let's take an example where we are opening a PowerPoint presentation from an SSD. In this case, SSD is connected. Let's say here you have connected SSD to the PCI controller. Then SSD controller does the device detection at the SSD interface. See, there is some kind of device detection happens through which the PCI controller or the root complex knows that one device has been connected into the topology. Okay. Then what would it do? It would generate an interrupt to the uh, interrupt that would be directed to the generic interrupt controller, what we are calling as the JIC, or it could even go to NVIC in case it's a Cortex M based processors. Interrupt gets generated to JIC or NVIC on a specific vector number. Processor loads and executes the corresponding ISR. So this interrupt will further be given to scheduled to one of the processors. That is, as we discussed, it would be done by operating system scheduler to decide which of the CPU cores that interrupt should be forwarded. So once that interrupt comes, the CPU knows that I'm getting interrupt on this particular vector number. So it knows what is the corresponding interrupt service routine. That is the set of instructions it has to execute in response to the interrupt coming in. So the corresponding drivers, I mean, when we say driver or the interrupt service routine, also we can call it a set of instructions are loaded to the DDR and they will be executed, which are already present in the DDR. They will be executed. So these are drivers specifically coded for doing transfers with the SSD. Now that it knows that SSD has been connected, so it will load that corresponding drivers and it will start executing those instructions as per the drivers. Now those drivers can include the what is the drivers will include. So let's say drivers are present in LPDDR5. So those drivers are nothing but some kind of assembly instructions which will ensure, which will configure the PCI that is present here to generate the transactions for writing to the SSD, reading from the SSD, generating flush kind of instructions. So depending upon what technology we are using, let's say we are using NVMe technology. For example, we are using NVMe based connection here, NVMe over PCI Express. In that case, my drivers will enable the processor to program PCIe controller, that is the SSD controller, to generate transactions in a NVMe packet format. NVMe may involve NVMe writes, NVMe read protocol, NVMe flush commands. So different kinds of commands will be there. So these instructions that are present, what we are calling as the drivers, when they're read by my A15 processor, will be generating some register writes and reads to the registers that are present in SSD controller, which in turn generates NVMe writes, NVMe read, NVMe flush, different kinds of commands could be there. Those commands gets generated, and those commands will be carried through the PCI link, and then my device understands that I'm getting write read flush command. Accordingly, it handles the things internally. So here I was trying to emphasize the significance of a driver. So what is a driver is, it's a set of instructions which will all be present in ARM instruction based. Okay, when those instructions are fetched by the one of the core, it starts getting those instructions based on the current program counter value in an incrementing manner. And once those instruction comes, it has got the fetch, decode, and execute. Fetch is for fetching the instruction corresponding to the program counter. Decode is to understand what is the thing that is coming. Because let's say if we have an instruction called as add R1 R1 R2, let's say something like this, R1 R2, just an example. So when it is doing add R1 R1 R2, so it is telling that add R1 and R2 and store it into R1. So it won't go as this add instruction here. It goes in some hexadecimal code called as the opcode. It's a 32-bit opcode or 16-bit opcode. If it is typical ARM state, it will be 32-bit. If it is thumb, means reduced size, it will be only 16-bit. So that instruction, when it goes here as a hexadecimal code, the A15 processor here decodes that hexadecimal number, 32-bit hexadecimal number, and understands that I need to do add R1 comma R2. So it internally does it. So here R1 and R2 would refer to the general purpose registers that are present inside the A15. There will be some category of instructions called as load and store instructions. Load command and store command. Okay. Load is for loading the register. Store is for storing the content of register into the memory. Those two registers will invoke transactions to happen to the memory. So let's again summarize everything. So you have a driver that is, let's say the PowerPoint presentation itself is the driver which is present in my SSD driver. Okay. As I said earlier, once you have invoked PPT, what happens if that PPT is already present in the DDR? It will be no need to get from the SSD. If it is not present, through means of DMA controller, that PPT specific information will be moved into the LPDDR3, and that PPT is nothing but series of assembly instructions. So when you, as a user, when I go here in the down, do PPT, for example. So what is happening is in my operating system, there is a scheduler is present. Scheduler decides that I should hand over this work to this A15 processor. So when I do that, what happens is it has got one program counter. That program counter will be assigned with a new value. What is that new value? Wherever this my PowerPoint application instructions are present, that value will be set to the program counter, and it starts executing the instructions from there. Okay. And it starts fetching the instructions through a particular path. I mean, in this case, it has got a dedicated path so that the bandwidth can be, I mean, latency can be reduced. In that, what is the significance of L1, L2? We'll discuss as a separate topic. But at the top level, my A15 knows that I need to run an application. Please give me 1 minute.
This conference will now be recorded.
So I was telling that the operating system scheduler will schedule that application to be run on A15. In that case, what will happen? This program counter, which is corresponding to A15, each processor has its own program counter. The program counter corresponding to this A15 processor will be set to the new value. What is that new value? That is the value, that is where my PowerPoint application is present. The instructions are present. So after that, A15 knows that I have to start fetching these instructions from here and starts getting and starts executing. And these instructions, some of them involves internal arithmetic operations. Some instructions would involve reading the data from the memory, writing data to the memory. That is where we would see the AXI transactions happening here. You see, one thing we want to notice here is that the instructions that are run by A15 could be two types. Some instructions which involves only internal things only. For example, you are doing addition, subtraction, multiplication. They don't really generate any transactions here. Whereas there are two separate category of instructions called as load instruction, store instruction. The load instruction would result in loading a data from here into the register. Store instruction would involve storing the register content back into the memory. So that is where actually my AXI transactions would happen here. Somewhere here, it could be anywhere. You see in AXI we'll have write and read happening. They will be the outcome of those load and store instruction. But any internal ALU related things, right? Add, compare, subtract, multiply, all those things will not generate any transactions here. So this is a brief about how the flow works. Now the program execution, that is the program counter jumps to this driver location. Instructions that are part of the driver will get executed, fetch and execute. And the AX and HB based transaction get generated during the load and store instructions that are fetched from the driver. Yeah, Nilesh, please ask your question.
Yeah, Sreenivas. So this SSD is the external drive we are connecting via PCI, right? Now,
Yeah.
in this case, you mentioned like the drivers get loaded into the LPDDR, right? But we know, I mean, the same operation has to be done multiple times, right? So in that case, because it's an external device, will L1 and L2 will come into the picture, or it will always take the route of, I mean, main memory? Let's say I want to
See,
do continuous write and read, right? So that program counter may give the address of L1, L2 also, right? If same multiple things we are, I mean, same thing we are doing multiple times.
let me clarify one thing here.
Mm.
From a processor perspective, okay, it primarily always access only the system memory. Now the system memory we are talking about could be LPDDR3, LPDDR4, any LPDDR. It could be DDR, or it could even be HBM, high bandwidth memory. Okay, let's assume I have one more thing called as high bandwidth memory, even in wide IO here.
Okay.
This is all part of my system memory. Okay, processor always only directly interfaces with the system memory only. It never runs or executes instructions from the storage class. Means let's say I have SSD or HDD. It never fetches the instructions directly and executes them. Now coming back here, let's take an example of a little more complex one. You have got 100 gigabyte gaming application is there. My LPDDR3 is only assume 8 gigabyte. It is possible, right? I have 100
Yes.
gigabyte gaming application, whereas my LPDDR3 system memory is only 8 gigabyte. So in that case, what happens is my operating system has the intelligence to know which is the which part of the game I'm running right now. So let's say some part of the, there will be different aspects of the game, right? That part of the game only will be loaded here, and this my the operating system is aware that which part is loaded. Accordingly, those instructions only will be fetched. Once it is done, now I'll also answer your question related to L1 and L2.
Mhm.
L1 and L2 are not separate memories. They are just the copies of this memory. Okay. Let
Yeah.
me
Yeah.
give you one simple analogy to help you understand L1, L2. Uh, for example, you want to buy one milk packet. Okay. There are two options. One is you go to a local provision shop which is next to your house, or you go to supermarket to buy. So which one would you prefer? You would prefer going to provision store next to your house and get it. So that is like L1, L2 caches. Let's say you want to buy some jeans, for example. You will not buy from a local provision shop because they don't maintain, because you don't frequently buy. See, milk is something you buy every day. So what provision shop will do, they know that since you will be accessing frequently, that milk packet you will be buying frequently, they'll maintain their own thing. From where do they get that milk packets? Where, let's say you may go and buy only one packet. When they don't have it, they go and get some 100 packets from here, and they keep a copy of that 100 packets. So as you need, instead of you going and getting the things from this far, which will involve a lot of latency, the data comes from here itself. So in summary, if I have 8 gigabyte data here, whatever data that is present in L2 cache, L1 cache here is just one part of this data that is present here. It is not separate locations altogether. These are all L1 and L2 cache is always a subset of system memory, that is LPDDR or DDR memory.
Okay.
Okay. So now the question is, why not keep everything here itself, right? And so going back to the analogy, why not provision store has everything? Then that itself becomes a supermarket, right? So the point is, what provision store has its own limitation in terms of what they can keep and all that. So here the cost comes into picture. L2 cache is implemented using SRAM. DDR is implemented using SDRAM technology, which is much cheaper. So here you can have a much higher capacity. Caches will be limited in capacity. So that means you cannot keep all the data of LPDDR into L1 and L2 caches. It is not possible. So whatever data that you frequently access will be kept into L1 and L2 caches. And
Yeah.
1 minute, I'll clarify. SSD is the superset of LPDDR. Means if let's say my SSD could be 1 terabyte, that entire 1 terabyte cannot be accommodated into LPDDR, right? Only 8 gigabyte can be accommodated. So who decides that? My operating system decides. The overall operating system which is running, it has got a scheduler which decides currently which applications are being run. Let's say currently in my laptop, GoToMeeting is being run, PowerPoint is being run. So the corresponding application related data will be, instructions and data will be moved into DDR. In that also, whichever is frequently being accessed will be kept into L3, L2 and L1 caches. And it is all dynamic in nature. What is dynamic in nature is, after 10 minutes I may close my PowerPoint presentation, I may start playing some video player. So that corresponding application will be moved and the PowerPoint will be removed from the DDR. So it is all happens in a dynamic manner. Yeah, please ask your question. Any further things?
Yeah. So no, L1, L2, L3 different, I know, but my question was, let's say multiple times write and read I'm doing to SSD, right? So in that case, every time it has to take the long route till LPDDR3. I mean, because L1 and L2 is also replica of main memory, right? Few of the contents, not everything, right? So in that case, it can directly fetch from there, right? That program counter, because earlier what you have shown, you are showing it will go to LPDDR3. So my question was, every time it will go, or if it will get something from
Not
L1
every
or
time.
L2?
Not every time.
Yeah.
See, the protocols can have specific technology. For example, in PCI Express, when you are generating a write, right? When you are generating a write, there is a concept called as nearest cache or something. There is one feature in PCIe which enables, whenever you are moving the data, right, performing a write from here, getting the data from here, it can, instead of updating into LPDDR3, it can directly update into corresponding cache itself. That feature is also available.
Okay. Yeah. Because every time it will go, the latency will be more, right?
Yes.
Yeah.
So in that
I think
context only, PCI has one field through which we can indicate that whichever is the relevant cache, that can get updated also.
Correct.
I'm not
Just
able to I'm not able to recall that field or feature, but that is possible.
Okay.
yeah, just to add, right, Nilesh here. So the first time the access, it will be go via the DDR and it will fetch the memory and store it in L1. Right. So after that onwards, if it is the same data it is requesting, it will go via L1 or L2. But if it is other than data available, anything required other than L1 or L2, then again it will go. It won't go the always to the LPDDR.
Yeah, correct. So that's what I want to know, because you're showing every time it will go. So I thought maybe that for the external connected device, whether it's a different mechanism or what. Yeah.
Yeah, that's
Okay.
a coherency controller will be there. So that will be
Yes.
that knows that whether the requested data is already in L1, L2, then it will
Mhm.
not go inside there.
Yes,
Yeah.
yes, yes. Yeah.
So
Got it.
here's one question from my end.
Yeah.
So
Yeah.
basically, we are assuming already that our all PCI link and the DDR training everything and are up, and then we are looking into the example here, right?
Yes.
Oh, okay, sure. I just want to know like how the boot code or boot loader will happen, so that you are going to
No,
cover here.
bootloader will take care of that actually.
Okay, so how is that step actually? That also will be external to the uh, like
No, see,
system.
bootloader will be particular to the system, right? You know that in your SOC, for example, if you take this scenario, for you to move the data from here to here, okay, that data will not be moved by A15. Processor won't do that. For that, there is a particular component called as DMA will be required. So
Oh,
for this entire thing to happen, what should be minimum happening? This interconnect clock should be up and running. This clock should be up and running. This system DMA should be up and running. DMA should be enabled. Then
got it.
the PCI clock should be enabled. LPDDR3 should be up. The 5 should be configured. The clock should be running. So that bootloader will have all that essential required instructions to enable this to happen. And who does everything? There will be one clock controller logic which need to be programmed to enable the clocks for everything. So that minimum set of instructions that are required for system to work will be part of that bootloader logic.
Okay, that will be stored in some of the memory inside the system only, right?
Yes, no, it will be part of a flash memory.
Yes,
Okay.
yes. So can you explain
See,
in detail more about the flash memory loading, which has the
I
boot?
will cover that in the bootloader topic separately.
Perfect. Yeah, I just want to understand that.
Okay. See, the logic is generally how it works is boot code will be present in a ROM, bootloader will be present in a flash. This flash can be directly fetched by the processor, or in particular scenarios that bootloader itself gets moved into DDR. That bootloader, because for faster access, generally flash will be slower compared to DDR. So if it is a more complex bootloader, it will be moved into LPDDR, and from there it fetches. So let me explain this entire concept when we go to the CPU booting concepts.
Sure, sure. Yeah. Thank you.
Okay. Any other questions? Next. Let's also just discuss briefly about how this ARM training course that we are doing now differs from SOC training. As you're aware, our institute also offers one course on SOC verification. See, that is SOC design verification. That course is focused on SOC architecture, SOC features, and SOC test plan, very particular to SOC flow. Okay, and SOC test bench architecture, test bench component coding, the VIP coding, VIP integration, and how do we develop C test cases, and how do we develop system verilog part of the test case. And then we take one practical example, RISC-V based SOC test bench development we take, where there we learn how to develop test cases coding and how to debug those test cases, both from a processor perspective and from the peripheral perspective. And then we also try to understand the SOC boot flow. And in this SOC course, we also discuss about ARM and RISC-V instruction sets. You see, this is very, I mean, the one where we have designed for SOC design verification, it is very particular to SOC flow, where we are covering in a more practical manner by developing test bench test cases. Whereas the current course that we are talking, ARM course, is very particular to ARM architecture and ISA related aspects. Uh, Talking further about the SOC architecture, this is one more architecture. So the point is, I'm just trying to show you how does a typical architecture look like. This is another architecture which is of OMAP 3630 that was a TI mobile platform long back they had. So I just taken that one of that as a reference diagram. It has got various components connected, though it is not shown through the interconnects, but it has got all the essential components like high speed controllers, the display controllers, video DAC, USB, UART, SDIO, so which are all required for the mobile SoC subsystem. That mobile SoC, ARM Cortex, they have hardware accelerators, signal processing, all those things are there. Okay. Sure, Abhinav, I can cover PPC 440 as well. Okay. Next. Talking further about SoC verification overview, which language to develop test case? I mean, this is a brief about SoC verification before we deep dive into ARM architecture as such. Okay. In which language do we develop SoC test cases? Mostly we use the C language, execution targeted for the processor. Okay. SV. We use both the languages. The test case is developed using C language as well as SV. Whatever SV code we develop, that is targeted for the peripheral behavior. The C part of the test case is targeted for the processor execution. Okay. Why we use C language? I mean, why don't we develop in assembly code itself? C language gives a more algorithmic style of coding. As you are aware, ARM course only understands the machine language. Okay. In this process, whatever test case we are developing through C code, that will be converted to hexadecimal opcodes. So the processor fetches opcodes from the DDR, and the CPU decodes. Opcode, as I said earlier, is a hexadecimal number. The CPU decodes the logic from the opcode. And for example, one of the opcode, just an example, 25647892, a hypothetical number, could mean add x0 x1, something like that. So it could translate into this kind of instruction. The test case will be developed using C. Why not assembly code? I have already explained you, because the C style of coding provides algorithmic way of coding. Whatever register writes and reads we want to do, memory writes and reads you want to do, you can do in more algorithmic manner rather than working at the instruction level. This can be reused for other processors. I mean, whatever you are developing in C language can be used for different processors, whereas whatever assembly coding instructions we develop, they will be particular to that processor only. Compiler specific to that processor is only required. So when you develop your test case using C language, that will be given as an input to the compiler specific to the processor, that converts that C code into corresponding assembly instructions. So whatever C code, when you give as an input to C compiler, it generates assembly level instructions. And C code provides ease of debugging, because it's, as you see, it's more like a algorithmic level we are writing. So the debugging can be easier when you develop test case in C. Next. As I said, test case developed using C language. Just an example, you want to develop a test case targeting DMA transfers from a source component to destination memory. You want to move data from SSD to DDR, for example. As you know, it involves some series of register writes and reads. I mean, we need to configure the DMA by setting up the DMA buffer descriptors, okay, to move the data, right? So in that case, the processor configures the DMA controller to read data from a particular location and write data to particular location. Okay. So these register programmings, whatever we are developing in the test case, can involve 4 types of accesses. Writing to a register, I mean, from the processor perspective, it can do only 4 things. It can be either writing to a particular register in the DMA controller, or reading a register, or it could be writing to a memory location or reading to a memory location. Okay. My test case would involve these kind of accesses. When that is given as an input to the compiler, it generates the corresponding machine code through the process of compile, linking, and assembly. So compilation will be done through ARM CC, linking will be done through ARM linker. and there will be something called as scatter file, which indicates how this generated code and the variables related to my program, whatever program I'm executing, these will be stored into the memory. When I'm storing all the information into the DDR, at what part of the memory read write related variables will be stored, at what part of the memory read only related variables will be stored, where the executable code will be loaded. So all that will be indicated through scatter file. So what exactly is the scatter file and everything will again discuss in a separate session. Okay, so this was to just to give you a top level overview of the SOC verification. Let me brief again. So whenever we are developing a test case for specific feature verification in SOC, the test cases will be developed using C language because it provides more intuitive way of looking at the things rather than developing in assembly level programming. Mostly these test cases, whatever we develop, will involve 4 types of accesses to be generated by the processor. Either it could be writing to set of registers, reading to set of registers, or writing to memory locations, reading to memory locations. For that, the SOC environment will have few methods, some kind of C functions, like write reg32 could be one method. Like let's say we want to write to a register, there could be one method called as write reg32, where you give address 1234 1234 000. Let's say you want to write 1111222222. This is the data that I want to write into the memory. Or I could be doing something like read data, read a particular reg. Let's say read reg32, one control register I want to read. Let's say control register, value of the control register. Okay, so like this I can have few methods for writing to a memory, reading from the memory also. Write mem32, something like this could be there. So my test case will consist of these kind of series of register write and read calls. When this code is fed as an input to the compiler through the process of compile, link, and assembly, machine code gets generated finally, which is a uh, hexadecimal code, which consists of hexadecimal code. This code will finally translate into whatever we have. This code can translate into some kind of image file, means test.image file. Let's call it as test.hex file. So which could be something like this. Like that series of codes. Okay, this image is loaded into the memory, and this is what we are calling as our applications. Even when we say PowerPoint application or even any applications that we are running on mobile, essentially that consists of some millions of such hexadecimal codes which are organized as some processes. Each application consists of multiple sub blocks, right? Each of them will have sub blocks like this. So as we run the test case, as we start the processor starts fetching these instructions. That is the opcode. This opcode, it understands that I have to do some addition, subtraction, or load, store, whatever, based on how this gets decoded. And that is how essentially the processor ends up performing a writing to a particular register, or reading a particular register, or writing to particular memory location. All that would happen based on these opcodes. So the whole point is, instead of developing the things at this level or even at the assembly coding level, the companies, everyone prefers developing the things at this level, which is more intuitive way of looking at the things. Then what is scatter file? I was telling you, scatter file is whatever this thing you are generating. This will also involve some writing and reading some data, right? How that memory will be organized. So the scatter file will tell if this is your DDR, this portion of the memory will be used for storing this instructions. This part of the memory will be used for storing the data variables. See, when you are doing some application, right, you will be storing some data. Just I'll give you one simple example. I ask you to add some 10 numbers, 112, 79, 65. What will you do? First you'll add two numbers. Let's say you added these numbers. What is that comes? 191. You will have to store that 191 somewhere. So that 191 will be stored here. You are doing addition, right? 112 plus 79, that is one of the instructions. Addition is the instruction. That instruction will be stored here. 119 will be 191 will be stored here. So some are read only region, means instructions you only have to read, you will not update the instruction. Whereas 191 will get updated after 191 plus 61, how much it will become? Let's say 256. Now 191 need to be updated to 256. So my DDR memory will be divided into few parts. One will be read write kind of part, one will be read only part. Okay, one is executable part. So that division, how you are going to divide your DDR and how you are going to place your application related instructions, application related data, it's all defined through scatter file. So this is a very brief about SOC verification overview. Any questions you have in all this?
Yes, Sreenivas.
Yeah.
Okay. So Srinivas, you said that the instruction is read only, right? So when we connect like a SSD, right, external one, right?
Yeah.
So that should be actually read and that should be written into the LPDDR, right? So
Yes.
if it's a read only memory, how we can write those instructions? That is the first thing. And second thing is this linking part. You are saying that hexadecimal files will get generated, right?
Yeah.
So how linker will help over there to execute that hexadecimal to, I mean, actually on processor?
Okay, fine. See, the first question about read-only portion is from the processor perspective. Processor cannot update instruction, right? See, processor can only read the instruction from the DDR.
Okay.
From a DMA perspective, it's a read-write. The DMA
Oh,
can read the data from storage and move the data into DDR.
okay.
We are looking from a processor perspective, it's only read-only region.
Oh, okay. So that kind of, I mean, whatever that uh, read write or read only, right? That kind of access we can, I mean, restrict via firmware or how it is. I mean.
Firmware, I don't think firmware. Probably the processor itself will have. Uh, yeah, it should be taken care at firmware level. Yes,
Okay.
where
Okay.
processor knows that this region is into falling into read-only region, it cannot
Uh,
write anything to that. Yeah.
okay. Okay. Got
Can
it.
you elaborate second question, please? I missed in the flow.
Yeah, that linking part, right? You are showing
Yeah.
that whatever opcode or data, whatever is there, right?
Yeah.
That will be that will generate some hex file, right? Series
Yeah.
of instruction.
Yeah.
So what is the role of linker there? I mean,
No, see
how
what
that?
happens. You take. Let's move to a simpler example. You are running a Verilog code. You have
Mm,
got 20 modules. Do you think all 20 modules will be present in single file? No, right? They're all
mm,
different modules compiled as different objects. Finally, what
correct.
happens? They get linked, right? During elaboration, what happens? All based on how they are instantiated in each other, they get linked. Something similar
Correct.
here we are talking about, because
Oh, okay.
all codes are not executed in a single file. In a complex SOC, we may compile one set of C functions, another set of C function as different things, and they are, and in C program there is no module. Everything is connected as functions, right? Set of function calls. So
Mm,
that linking is what I'm talking about. Yeah.
okay. And scatter file also will be decided by the architecture guys, right?
Yes, yes. Scatter file, see, with the processor itself, it won't come. See, scatter file is something that you define for your application. How do you want to? Why scatter file is important? Let me tell you. You are running one application. Uh, you want to store 10 variables, but you have given only enough space to hold 5 variables. Then it's a problem, right? So they need to
Correct.
decide how much space I need to allocate for read only region, for how much portion I need to allocate for read write region. So that is all decided by the specific to the application.
Okay, and like opcode and data we are storing differently, right? So
Yes,
let's say if you want to do some addition, right? So we need first we need to fetch the opcode and then data, right? And then we have to
yes,
store that data as well, right?
yes,
So so those all where exactly it has been kept into the memories, right?
yeah.
So that program counter who will control? I mean that in, because processor, how it will come to know I have to go to this particular location and fetch this opcode and take this data.
See, for fetching the opcode, it is the program counter.
Hmm.
See, fetching of opcode is all by the value of program counter. Now, fetching of the data is as per the instruction. For example, you may say one load instruction. I'm not writing exact instruction. Load R2 with a data from R3 hash something like this. Let's say in the bracket you write hash 100. Just not taking exact syntax, right? What are you telling? In R3 there is one content is there. To that address, to the content of R3 content, R3 register content, plus add 100 data. At this location, whatever data is present at this memory location, move this data to R2. Instead of move, let me call load this data to R2. Whatever content that is present at this address location in the main memory, move that data into R2. Now if you ask me who decided this R2, who decided R3, who decided 100, it is decided by the compiler. My compiler is smart enough to understand if this is the C program developed by user, it need to be converted into this kind of assembly instruction so that it gives the exact same behavior. So for that, we need to understand how that conversion happens. Let's say if I write simple example for integer I equal to 0, I'm not writing exact C language here. Okay, I less than 10, I plus plus. For example, if I write int array, sum equal to int array of plus equal to int array of I, let's say. I'm sure you understood what I'm doing. I'm adding the integer array. Okay, 10 numbers. So this is what you would write when you give this code as an input to the compiler. So compiler knows each integer. Let's say you would have even told where is that array is present. Let's say array is present at location starting from 100 onwards. Next will be present at 104, next integer 108. So it would generate the code in such a way that my compiler will generate the assembly code in such a way that every time you're adding, it would start fetching at 100, next time it will fetch at 104, 108. That kind of that kind of automatic code generation will happen.
Got it. Okay, compiler should be smart enough to, I mean,
Yes,
have all this
compiler
knowledge.
is designed to understand how to implement the for loop. For example, for loop it will use a concept of label to keep moving. Then if for this purpose it knows that it has to compare and accordingly branch whether to go inside or whether to branch out of the for loop. It knows that entire conversion compiler will take care.
Okay, got it.
So in this entire process, what is the processor significance? Let's briefly understand. See, processor is the point of interface between firmware and the hardware. Anything that has to happen between firmware and hardware, or even you can call firmware or upper layers, even we can call the software, operating system, applications. You call anything, if they have to interface with the hardware, it always has to happen through processor only. It means if I need some transfer to happen here, PCI to SSD. Okay, I mean SSD controller to SSD storage. My operating system cannot directly inform to PCI. It is not possible. Everything has to be going through one of the particular processors only. So how does it do? It's how it happens by making sure that the corresponding program counter is changed to the required application code. Then it starts executing those instructions. In summary, anything that we want to do from the upper layers, the firmware, operating system, or software anywhere, they all have to get the work done through this component only. So in between the operating system and this hardware, we have got scheduler, which decides how that activity should be distributed. So as you are aware, whatever user applications, they will interface with the operating system. Operating system interfaces with the firmware interfaces with the hardware, and ARM processors are based on RISC architecture. So this was a very brief about SOC verification flow, and very little brief about how the C test cases are developed, everything. Let's now talk about RISC versus CISC architecture, and then once it is done, we'll go for a break. So let's start with understanding of RISC architecture versus CISC based architecture. Okay, as you are aware, RISC stands for reduced instruction set computer. Okay, reduce the cycles per instructions at the cost of number of instructions per program. Whereas CISC is a complex instruction set computer. Okay, so here, as the name itself suggests, the instructions are complex. Okay, here reduced instruction means what? You simplify the instructions. You keep the instructions simple by reducing the number of cycles per instruction. Whereas complex instruction means here you're increasing the complexity of instruction so that effectively you do the same work with less number of instructions. Since you are reducing the complexity of each instruction, to do the same work, you will take more number of cycles with RISC. In CISC approach, attempts to minimize the number of instructions per program, but at the cost of increasing the number of cycles per instruction. I mean, same work, here you will take more number of instructions, but each instruction will be simpler. Here you will take complex instructions, but fewer instructions. Because you are taking each instruction is complex, you can finish the same work in fewer instructions. Tell me, looking at this, which one do you think offers more efficiency, RISC or CISC?
CISC.
Efficiency in the terms of can you repeat that? Means what efficiency we are saying?
See, in RISC, what happens is, let me explain. RISC will only have, let's say, RISC will have 100 instructions. Just an example. CISC may have lesser number of instructions. I mean, in case of RISC, what happens is each instruction gets over in fixed one clock cycle. Except for maybe there could be special category of instructions like SIMD instructions. There is a category of instruction called a SIMD. Except for those kind of things, whatever instruction you do, it is compulsory to get over in one clock cycle. Whereas in CISC, each instruction may take more than one cycle, one clock cycle to execute. Here, same work, instead of program or same program, let's call more technically, same program will require more number of instructions to complete. Here, same program will require less number of instructions to complete because we are keeping each instruction complex. One instruction itself is doing multiple things. Means one instruction itself does multiple things. Because it does multiple things, okay, with few instructions only you can complete the same program. I asked a question, which one do you think will be more efficient from a processor designing perspective? Which one offers more efficiency from a processor designing perspective?
Srinivas,
Yeah.
CISC is nothing but a series of risks, right?
Series of risks. You
Because
can,
to execute one complex instruction, you need to
yes,
have multiple simple instructions, right?
yes, it is
Execution.
further broken down into internally. CISC will break down the complex instruction into individual instructions only,
Mhm.
right? But if you look from a processor design perspective, see how the processor efficiency has been increased over the time, over the different architecture through an important concept called as pipelining, right? One of the things that has been used majorly is pipelining concept. See, the risk offers more definitive thing. So see, because you know that each instruction will take only one cycle, you know that when I'm fetching an instruction, let's say I know this many cycles it will take to fetch, you know that I'm decoding, I'm executing, you know how much time this will take. Definitely next one, let's say next instruction you are fetching here, decoding, executing. So there is a definite relation how the instruction flow will happen. That kind of thing won't be so definitive in CISC, because each instruction takes different instructions take different number of cycles. For example, you take the same thing, one may
Got
take
it, Srinivas. Got it,
more
got it. So
time.
for pipelining perspective, you're telling about efficiency, is it? So when we come in terms of power, then which one will be good?
Even from power perspective, risk is better.
I see. Okay.
Yeah, that is where you see all the mobile phones, everything we are using risk based things only where we are not really too much concerned about power, we are going with CISC based architecture, x86, even laptops, all that, right? They consume a lot of power, right, compared to mobile phone. So they are based on CISC. So in the
But
power efficiency,
performance-wise, how about performance?
performance wise, of course CISC gives more
Good.
higher performance. Yeah.
Got it. Okay,
I think
Srinivas.
risk is catching up, but currently as it stands today, CISC of course offers higher performance, but at the cost of uh, this thing, processor design efficiency in terms of power consumption. Risk provides more advantages. So let's discuss more deep into a little more into each of them, what exactly each one offers. See, let's say we'll take an example of adding two 8-bit numbers. CISC approach will be what? See, it will just use a single command or an instruction for like this add, which will perform the task. I mean, one add itself you do, in the add itself you tell something like this. Add something at location 100 with something at location 200, something at 300 location. I mean, you are directly telling that add the data that is present at location 200 with the data that is present at 300, store that information into 100. Whereas in risk approach will be, first it will be implemented in 3 stages. First you will have to move the data that is present at 200, get the data, load the data into one register, load the data that is present at location 300 into another register. Then you have to perform add. Then that data will be moved, whatever is the result data, that will be moved into location 100. So the same one complex instruction is broken down into multiple smaller instruction. But one thing you know that whatever 4 instructions you did, moving data from 200, moving data from 300, adding, and then storing the data back into 100, they will all take only one cycle only. So there, the pipelining of those things becomes easy. The load command to load data in registers from the memory, add operation, then store the result into desired location of the memory. A risk architecture uses simple execution with each instruction taking only one cycle. Example, 50 instructions, you know that they will take 50 cycles, 50 clock cycles. So it is based on load and store architecture. What is load and store architecture means? You know that assembly instructions will be various categories: arithmetic instructions, branch instructions, right? Floating point instructions. In that there will be one category of instruction called as load instructions and store instructions. In risk architecture, only load and store instructions only can access the memory. Okay. The load and store only can access the memory. all arithmetic instructions, for example, you are doing add, subtract, they cannot access the memory. They can only access the register contents. That is, general purpose registers will be there, right? Those will only be accessed. If you do add, you cannot specify a memory location in that instruction in case of RISC. Okay, so majorly you can categorize instructions into two categories. One is the memory access instructions. The load and store between memory and registers is where memory will be accessed by these two kind of instructions. That is the load command, store instruction. Load instruction, store instruction can access the memory. The other things are like ALU operations, which will only occur between the registers. So let me summarize again. In case of RISC architecture, the ALU specific instructions like add, subtract, multiply, compare, they can only happen with respect to the registers. They cannot access the memory. CISC instructions can access memory locations. They will use complex instruction. Each instruction might take more than one cycle. Example, if you are running 50 instructions in CISC, they can take more than 50 cycles to execute. So there is no fixed thing that they will all take only 50 cycles or 60 or 70. It is all completely variable based on which instruction you are running. Because of that, pipelining becomes difficult. See, pipelining is easy when you know that there is a fixed time that is being used for each instruction. Because each instruction takes a variable number of cycles and complex instructions, it becomes difficult to optimize the processor performance and difficult to implement the pipelining. And ALE instructions can also access the memory locations as we discussed. Okay. Let's now briefly talk about this adding two numbers example once. Okay. In case of RISC, load value from memory to a register, general purpose register, you would do something like this: load x1 hash 100. So from memory location 100, you're loading the data into x1. So you see here, you're accessing a memory location through the load instruction. Then from location 200, you're loading data into x2 register. x1 is a general purpose register. x2 is a general purpose register. Then you're adding contents of x1 and x2 into x3, storing the result into x3. Storing the results of x3 back into 300 location. Each instruction completes in one cycle. You know that this will all take 4 cycles. You can even do pipelining at this stage. So while this is being executed, you can fetch this instruction. While this is being executed, you can be fetching and decoding this instruction. So that way you can pipeline and complete them quickly. What is the drawback of this RISC approach? Code density will be more, because to do the same work you are using, to do one adding of two number work, you are using 4 instructions. Above 4 instructions require 16 bytes of image, because each one is 32-bit opcode, that is 4 bytes. 4 into 4, 16 bytes of image will be required for this instructions. In case of CISC, add 300, 100, 200. CISC allows operands to be arrays also. There is one more convenience in CISC. You can also write arrays also here. So processor directly fetches the data from memory at both 100, 200 locations and then add. It is internally dividing it into same thing. I mean, it's nothing different. It is actually internally dividing into load, store only, all that. But it is giving me flexibility to write at a top level. Then store the result to destination. An instruction may run for multiple clock cycles. Here we are talking briefly the difference between RISC and CISC on a point by point basis. Okay, before that, yeah, Priyanka, please ask your question.
Hey, Sreenivas, effectively, just a quick question. Effectively joined at 11 o'clock. Just was curious where this recording will be placed at.
I'll be giving access through the eLearning portal. This being a demo session, it will be placed on YouTube. Otherwise, you will get access through the InSkill portal.
Oh, so this recording will be there in InSkill, right?
Yeah.
Fine. And I know because all of us have registered, InSkill has this arm as a part of our curriculum, right?
Yeah.
I mean, okay. Thanks, Sreenivas.
Thank you.
I didn't see it yesterday night. I checked. The arm still didn't come up. So hence checking.
Oh, no, I will check, ask our team to enable the access. Yeah.
Sure. Thank you.
I mean, team was not working yesterday because of Karnataka Rajyotsava. Otherwise, they would have done. Okay.
Oh, sure. Please get it done
Okay,
whenever
sure.
possible. Yeah, thank you.
Okay. So let's briefly understand the difference between the risk and SIS on a point by point basis again. The risk uses a small set of instructions of uniform length. See, number of instructions in risk is less. Okay. Small set of instructions, they are of uniform length. Whereas SISC uses large number of instructions of variable sizes. See, number of instructions will be more. Okay, because you don't have smaller breakup. Each instruction will be implemented as a complex set. They are of variable sizes. In risk, if you take example of ARM v7 architecture, all instructions are encoded as 4 bytes. That means each instruction will be converted into 4-byte opcode. Whereas in IA32, okay, 32-bit instruction architecture of x86, they can be anywhere. The size of instruction can be anything from 1 to 15 bytes. The size of instruction itself is variable. It can be 1 to 15 bytes. In risk, only load and store instruction can access the memory. Instruction generally executes in one cycle, makes it possible to have multiple stages of pipelining. Whereas CISC, all instructions, majority of the instructions can access memory. Architecture includes a complete set of special purpose circuits that carry out instructions at a very high speed. Okay. Example, copying an entire block from one part of the memory to another and other. That copy of multiple registers to and from memory. So for that, there is a special purpose circuit that will make sure that the instruction is executed. Okay. Risk does not support an array. Risk instructions don't support an array. Everything has to be singular variables on singular values only. Whereas CISC instruction, you can pass as an array as an input to the CISC instruction. I mean, CISC instruction operand can be an array. And risk uses more general purpose register because it need to do lot of processing on the register data on all the instructions you write. You will be writing arithmetic, everything will be written through registers only, right? Whereas in CISC, it uses less number of general purpose registers because whatever instructions you are writing, you are directly targeting the memory itself. Because of that, it generally uses less number of general purpose registers. What are the advantages of the risk? It is relatively simple to design and inexpensive. Pipelining is easier. Okay. What are the advantages of the CISC? Reduces the program size because you are using more complex instructions. So the overall number of instructions required will be less. It effectively reduces the program size. Hence, the less number of cycles, memory cycle required to execute the program. In essence, it increases the overall execution speed because you are able to get the data quickly, get the program instructions quickly. It helps improve the execution speed. Now, coming to drawback in the risk, computer has to repeatedly perform simple operations to execute larger program having a large number of processing operations. One drawback of CISC will be it is complex to design and it is expensive because the pipelining concept can't be implemented simply in a simpler manner. So it requires some kind of special purpose circuits. So that makes the CISC more complex and expensive. Okay. So this was a brief about the risk versus CISC architectures. We'll go for a break now.